It's ridiculous. I'm not a dinosaur believer.
I mercilessly ridicule anyone who's British. Are credulous idiots. Big dinosaur. Clearly invented dinosaurs just to sell dinosaurs.
That's enough.
Music. The music.
No gangsters.
The music. The music. The music. The music.
Diatomic hydrogen can slip through microscopic pathways or even permeate a metal lattice to create its own.
It's not safe if you need to ask. If you need a mask, back to basics.
Just like Houdini, hydrogen can escape from steel.
Creates its own escape.
At temperatures above 1700 degrees Celsius, molecular hydrogen can dissociate into
atomic hydrogen.
However, on metal surfaces, hydrogen can dissociatively absorb at much lower temperatures. In the Haber-Bosch process, nitrogen and hydrogen react over an iron-based catalyst at about 400 to 500 degrees, pressures between 100 and 250 bar to form ammonia for the fertilizer industry. These high pressures require large, high-strength steel pressure vessels. One problem is that under these conditions, atomic hydrogen can diffuse into the steel. This can lead to hydrogen embrittlement and, at elevated temperatures, high-temperature hydrogen attack.
displacing anything that's bonded to the carbon. If it can come in contact with 4 carbons, either via loose carbon or iron carbide, then it can form methane.
Larger molecules cannot diffuse out easily. It accumulates at grain boundaries and within microscopic voids.
Ultrasonic scans show a cloudy appearance. At first, these are microscopic bubbles, which coalesce into very tiny little bubbles, which lead to tiny fractures throughout the metal.
One non-destructive method of detecting this is with a phase array of ultrasonic transducers.
Timed in such a way that their combined backscattered signals are focused, reducing noise and producing an accurate image of any internal boundary within a material. A hydrogen bubble or methane bubble
trapped within steel appears as a reflective boundary to the probe as it cleverly sweeps through the material. By adjusting the timing, the system can change both the inspection angle and focal distance, plotting the resulting data points as a heat map for safety inspections. Hydrogen attack and hydrogen embrittlement are common concerns across many industries. The strength and quality of welds are also greatly affected by gas inclusions and voids. Here you can see one of my laughable first attempts at stick welding, which serves as a prime example of this.
It's a hydrogen attack. Feel the pressure and the energy. Surfaces are glowing, all the molecules are jiggling. When it's hotter than a heat wave is when the hydrogens attack. Yeah, the hydrogen attack, that's a fact. And you don't want that. Backscattered, out of phase, ultrasonic graph shows methane on a Soft
inner layer,
The
hard
inspector
outer
says to
layer.
shut it down. You know there's been a hydrogen attack.
One form of mitigation is to use chromium-molybdenum steels. Chromium and molybdenum form more stable carbides, tying up the carbon.
Making it less able to react.
If you're like me, when first encountering a metal described as a steel mixed with chromium, it might make you think, that's probably one of those grades of stainless steel, such as 304, 316, 430, 409, 410, 420, 420, 420, 40, 2205, 2507, or 74 pH. Each of these is a unique, task-specific variant within the ferrous metal alloy subgroup known as stainless steel, containing, by definition, at least 10.5% chromium. Allows stainless steel to form a protective passive oxide layer, offering protection in wet, oxidizing conditions. Alloys with 9% chromium or less are generally referred to as chromium alloy steels or low alloy steels. While they can still resist oxidation in dry, high-temperature environments, they trade some of their corrosion resistance for increased strength and hardness. The most high-end, ultra-premium, top-tier, and demanding industrial plants often build their reaction vessels from Inconel. Instead of being iron-based, Inconel is a nickel-based alloy often containing molybdenum, niobium, cobalt, and aluminium. Because nickel's crystal structure is face-centered cubic, it does not undergo the temperature-dependent phase transitions seen in iron. As a result, it retains its toughness and does not become brittle at elevated temperatures. The protective oxide layer it forms is strongly adherent, so it does not readily flake or spool away. Inconel is an expensive family of superalloys used when conventional materials cannot meet the required performance standards. It is used in applications such as chemical processing equipment, gas turbines, jet engines, and rocket nozzles.
Yes, this is the new acid. High pressure, heat catalyst. Structural integrity confirmed for massive scale. Watch the throughput rise. Watch the output reach the skies. The new infrastructures yield.
The catalyst in the Haber-Bosch process is responsible for lowering the activation. The process uses an iron catalyst, typically promoted by adding small amounts of potassium hydroxide, aluminium oxide, and silicon dioxide. This increases the efficiency and lifespan. Of course, the catalyst does not change the percentage of the yield, nor does it get used in the reaction.
The global fertilizer industry got its nitrogen from sodium nitrate and potassium nitrate, from mined out of the ground, mostly in Chile.
Saltpeter supply wasn't expected to last more than another 30 years.
Civilization-wide famine was largely averted thanks to Fritz Haber, whose synthetic ammonia process helped feed billions. In a remarkable display of cosmic balance, he is also remembered for pioneering the use of chlorine gas as a chemical weapon during World War I.
A man whose genius saved billions, a man whose patriotism poisoned thousands.
But to get back to hydrogen.
The chromium-molybdenum steels used for many high-pressure hydrogen vessels contain significantly less chromium, typically in the range of 1 to 9%. At these concentrations, the chromium is not primarily added to provide corrosion resistance. Instead, it improves the steel's high-temperature strength and promotes the formation of stable carbides that help resist hydrogen attack and embrittlement.
It also quantum tunnels, though there's really no hope in trying to contain the smallest, lightest element. H2 of the atom.
Although hydrogen is diatomic, it is really small. It has no need for any fancy neutrons, just simply carrying dead weight. It lives a different way to its heavier isotopes, deuterium and tritium, with their materialistic wants and vices, either trying so hard to be isoelectronic to a higher rank on the table, or like tritium, always trying to be the cool guy at the cocktail party.
I'm so hot and radioactive, I hang around with those nuclear physicists.
None of that inflated ego and mental baggage. Hydrogen, yes, he's diatomic, but he's simple, steady, and light-footed like a shinobi. Like a silent ninja. Leo from the Matrix. Legends say he can quantum tunnel through solid objects, tap in and literally borrow energy from the vacuum of space itself. It's not far off the truth. He can meditate himself into a state where quantum mechanics lets it tunnel through barriers that heavier atoms can only dream of crossing.
S&P orbitals. Examples so far I've been showing is as basic as it gets.
Ground state orbital hydrogen is until we move on to carbon. It's a good place to start. Check out these moves. Diatom is getting swifty. He's a proton in a shell.
As we learned in part 1, an orbital is an electron probability cloud, defined by a standing wave of constructive interference that occurs within the electrostatic potential of a positively charged nucleus, and only at permitted energy levels. These are drawn as orbital lobes that specifically map out where we can expect an electron to be with 95% certainty. Quantum mechanics gives the electron a non-zero probability of being anywhere in the universe, but it is vastly more likely to be within its associated orbital. You will see later that we can have many orbitals, but a single orbital can contain at most 2 electrons, and these must have opposing spin. Spin up, spin down.
The Pauli exclusion principle states that no two identical fermions.
Haha. The Pauli exclusion principle states that no two identical fermions may occupy the same quantum state simultaneously. Without this fundamental principle, we would not have solid matter, we would not have chemistry. Matter would collapse, and electrons would spiral in towards the nucleus as they lose energy. It is the driving force behind electron degeneracy pressure, which supports white dwarfs and neutron stars against gravitational collapse.
Because a hydrogen atom has only one electron, it readily pairs with another hydrogen atom. Their atomic orbitals merge into a molecular orbital to share those 2 electrons. The next element on the periodic table, helium, already has 2 electrons, meaning its valence orbital is entirely full. While both diatomic hydrogen and helium exhibit the weakest intermolecular forces on the periodic table, helium's are even weaker. A London dispersion force relies on the ability of an electron cloud to be temporarily polarized by its environment. Because dihydrogen has an elongated shape, its electron cloud is more easily distorted. Conversely, the smaller, highly compact spherical orbital of helium resists this polarization so effectively that it remains a liquid even at absolute zero, exhibiting the zero viscosity phenomenon known as superfluidity.
Slow its vibration and heat climbs walls. You want it fluid. This is a frictionless superfluid.
S&P.
From the quantum world, this special report. S orbitals are perfect spherical symmetry. P orbitals are dumbbell shaped with a planar node. Electron probability, density, all at the speed of light.
The capital gains are up, but the overhead's on sanity. I swear, the next generation will be taxed on original thought alone. Why does everything require 7 layers of non-fungible bureaucratic oversight? Why can't the entire world just embrace a collective consensus on the non-binary spiritual value of moss? Arthur's profits are hurting the vibes. The very atoms of the universe are experiencing secondary shame. Are those tax code books made of trees, Arthur? Dead trees that died to document your dead profits? These are digital print duplicates, from the same printer you used to print those collective consciousness visitations leaflets. We recycled them. With intention, each leaflet was a prayer for a more fluid future, Arthur, the consensus of the global soul. I'm trying to connect you to the whales, Arthur. They are calling for a more gender-fluid approach to corporate tax liability. Legitimate business? Arthur, that is such a heteronormative capitalist patriarchal linear way to view existence. Arthur, slapping his desk. Census on the whales is not a viable fiscal strategy.
It doesn't pay for the printer ink you use.
Printer ink is collective consciousness, and it is not a viable strategy.
This is methane. Simple hydrocarbon. This is a quick and easy way to represent it, but to actually start to understand how it behaves we need to pull this out into the third dimension. Only then can we see that it forms a pyramid shape. All the hydrogens have arranged themselves so as to be as far away from another hydrogen. Each are covalently bonded to the carbon. Let's first look at carbon on its own.
You will most likely be familiar with carbon as the most versatile atom. It even has an entire branch of chemistry dedicated to it. Organic chemistry. To understand the secret behind why carbon is so special, we need to look closer than just its standard orbitals. The true magic lies in the merging of these orbitals to form entirely new hybrid orbitals. Introducing hybridization theory. Depending on its bonding partners, carbon can rearrange and mix its valence orbitals to adapt. It can form 4 single bonds through sp3 hybridization, a double bond using sp2 hybridization, or a tight triple bond through sp hybridization. By creating these hybrid orbitals, carbon gains the flexibility needed to build everything from simple molecules to the complex chemistry of life.
Molecular.
Yes. So, we will be getting back to the concept of hybridization. Simply because learning this along with you is going to help us both visualize and ultimately predict the geometry of covalent molecules, what causes their specific shapes, what dictates the bond angles.
What's that? A new introduction. like a molecule shadow. What dictates the shape of shadow? It's a flat projection of a molecular geometry. VSEPR theory and Coulomb's law. Inverse square repulsion. Lone pairs from the outer shell. Repulsive floating clouds of negativity.
First.
Steel.
Steel.
Steel. Versus
The nickel superalloy. I've decided to bulk this out a bit more, but hopefully we can tie it in with orbitals at the end.
Most of us know that if we need a metal to survive extreme environments, we often turn to austenitic
Things.
It's tough, it resists corrosion, and unlike standard ferritic steels, it doesn't get brittle at cold temperatures. For example,
Fracture. And bend.
the cold temperatures of space, or like an industrial freezer. But when you push austenitic steel to the opposite extreme, it reveals a hidden flaw. Into the glowing heat of an industrial furnace or a jet exhaust, it drastically loses its ductility and brittles and cracks. Meanwhile, elements like pure nickel and its elite cousin Inconel, faced with the exact same glowing temperature, barely blinks.
Almost an ageless proton. Cyclotrons I used
to play.
Here we have a mechanical.
I've called
The tune. Ultrasound inspection.
Now they say I'm the fracture. Degrading way. Father, hear my confession. Slinging thing, yo. We called it the bomb. Got into steel. The iron. That poisons.
We call that methane. Bomb. Got my hands dirty in the steel dust. Felt like a damn thief in the trust. But now those ghosts all wear my face, leaving bitter ash all over the place. I burn all the plants, but I hear him sing his body-centered song. Nickel too stable, Inconel too strong.
Let's look at why the atomic architecture of steel breaks down under heat. To understand, we have to look at its microscopic shape-shifting act. It is almost more a concern of spatial geometry than mere matters of intervalent reactivity. However, it is empirical matter and it is the science of it. Zooming in to look at a unit cell. Pure iron at room temperature. This is ferritic and it adopts a body-centered cubic or BCC lattice. Body-centered cubic is 8 atoms that form an equilateral cube, all 90-degree angles. Fine. Body-centered means that there is also an atom in the center. Now then, if we start to alloy this with other metals, say 8% nickel, 18% chromium, we get a new crystal structure at room temperature.
Atom.
Primitive cell.
Primitive.
Primitive. Primitive.
If carbon hasn't already escaped as free carbon and crossed the border, that's what they do. It's because of the crystal enclaves, their iron matrix inadequacies. Their crystal vector and magnetic moments are always misaligned with the local grains.
Typical.
Their solubility is not their fault.
Carbon's welcome.
Not all carbons are bad.
Yeah. But having a carbon-inclusive open lattice policy when the temperature-sensitive lattice integration rates are known.
Today, we need to talk about a serious issue affecting iron communities across the periodic table.
Carbon. Now, before anyone gets upset, let me be clear. Not all carbons are bad. Some of my best steels contain carbon.
For too long, carbon has been blamed for problems that are really caused by iron matrix inadequacies. People say, oh, the carbon has formed enclaves.
No, those are not enclaves. Those are carbides.
Very different.
Well, slightly different.
Now over to Pete.
There has already been unrest, mostly in counties rich in chromium and molybdenum. The influx of carbon has seen disruption of the alloy, property destruction and division among the chromiums, with many choosing to leave with the carbon, resulting in chromium-depleted districts. And the controversial regions, chromium and molybdenum carbide precipitation along grain boundaries.
Carbon comes into the iron lattice looking for opportunity, a better life,
Higher hardness, improved tensile strength.
and what does it get? Restricted solubility, temperature-dependent, hostile
Neighborhood. The body-centered cubic lattice is clearly not designed for the inclusive interstitial living.
Ferrite lattice appears with a carbon atom awkwardly wedged inside.
Excuse me, is there room here?
Not really, mate.
Not really. You're distorting the matrix.
I'm literally smaller than you.
That's not the point.
That's not the point. And then people act surprised when carbon forms groups.
Tonight on Lattice News, growing concern in the ferrite regions as carbon atoms continue to cross crystal borders. Some have allegedly escaped as free carbon. Graphite communities have begun forming nearby. Authorities say they are monitoring the situation.
Increases hardness, enables steel, strengthens iron, good for tools.
Distorts lattice, forms carbides, causes brittleness, doesn't align with local grains. The anti-carbon lobby claims their crystal vectors and magnetic moments are always misaligned with the local grains.
Which is a very technical way of saying we don't like carbon in our lattice.
We support controlled diffusion, but this open lattice policy has gone too far.
It's easy for you to say. We have a face-centered cubic structure. We can accommodate much more carbon.
Absolutely not. Typical austenite elitism. At this temperature, this is where the debate gets ugly. Because at high temperatures, austenite says, we're progressive.
Come in. Carbon, we're face-centered. We're progressive.
Come in.
Carbon. We're inclusive.
Then the quench happens. There is no time for orderly diffusion, no community consultation, no phase transition paperwork. The carbon is trapped, the lattice distorts, and martensite is born. Martensite is what happens when a society cools too quickly. That sounded deeper than intended.
Now the carbon is trapped in a body-centered tetragonal structure.
And everyone acts shocked that the material is hard, brittle, and full of internal stress. You did this. You took a high-temperature, inclusive austenite community and quenched it into a stressed-out martensitic police state.
Pure metal, for better or worse, has had its own unique way of doing things. Proud heritage going back far as the Iron Age. Between 1200 and 1800 BCE is when we discovered how to smelt it. But it was in fact already a substance we had encountered. The Gurze beads were crafted as far back as 3350 BCE from a rare meteorite iron, and around 1323 BCE, Tutankhamun was buried with an iron dagger. This iron that came from fallen meteorites they referred to as the metal from heaven. It was more valuable and rare than gold, and had a high nickel content, making it more workable and corrosion resistant. It could be cold hammered, however, it didn't hold an edge, and its strength was inferior to that of bronze. Once it was found out how high iron's melting point was, the discovery of steel was accidental. The use of a cold furnace to reach the required temperatures meant they would sometimes unknowingly introduce carbon to the hot steel, resulting in changes in the material. These early iron smelting processes happened in Turkey, not Germany for once.
My fellow grains, we need sensible carbon policy. Not all carbons are bad. Without carbon, we just have soft iron wandering around, bending under pressure and achieving very little. But too much carbon, badly integrated, and yes, you get brittleness, carbides, and social fracture.
That is why we need heat treatment. Normalizing gives everyone a fresh start. Annealing allows tensions to relax. Tempering says, look, martensite, we understand you've been through a lot. Let's reduce some internal stress and become useful.
Exclusive interviews, real stories from exclusively inclusive sources. We're not in any way biased, like those other outlets.
Always biased, unlike us.
And not as diverse.
Diverse.
How did the quench make you feel?
Hard.
Anything else?
Brittle.
That's progress. So next time someone says carbon is the problem, remind them, carbon's solubility is not its fault. The lattice changes with temperature, diffusion takes time, and some phases are simply better at inclusion than others. Not all carbons are bad.
Don't invite 4.3% carbon to a ferrite and expect everything to remain ductile. That's not inclusion, that's iron. Subscribe for more socially questionable metallurgy.